Well, that was embarrassing. Video 9 did not exist. Uh, so what happened was I forgot to upload the video when I shoot it. So I made a video going through how I did what you see here, and I forgot to upload it. So that was a big fail for me. But anyway, I'm gonna work on this a little bit more for you. I solutions for number 1. I'll leave it here for a second so you can pause that if you want to and take a look at that. And then number 2 here, went through that. There it is. You can take a look at that and pause it. I'm going to do a couple more of these. Actually, I'm going to go to the back of this and do a couple more, like I said I was going to do, and that'll be video 9. So then you can work on it, okay? All right, so a boat initially traveling at 5 meters per second accelerates uniformly at a rate of 2.5 meters per second for 8.2 seconds. How far does the boat travel during this time? Okay, so kind of like we did in class, let's identify what we actually have here. All right, let me see if I can zoom in a little more. Just a little more will be all right. All right. Well, initially traveling 5 meters per second. All right, so that's the initial. Accelerates uniformly at a rate of 2.5 meters per second squared. Watch out for the units here, right? Because kids often mess this up. You see meters per second, you miss the squared. All right, so that's initial velocity, that's acceleration. 8.2 seconds, that's our time. How far does the boat travel? All right, I want to make my little organizational table here. 1, 2, 3, 4, 5. V initial, V final, V average, acceleration, displacement, and time. Now you should have your equation sheet handy. You've all been given an equation sheet now. Actually, I need to post that for the remote kids, don't I? Oh joy. All right, I gotta do that. It's I think I have it here. So V initial is 5 meters per second, 5.0 meters per second. V final we don't know. We know the acceleration is 2.5 meters per second squared. And we know the time is 8.2 seconds. So we're looking for how far does the boat travel. That's delta x. So our big unknown quantity is delta x. That's what we're looking for here. That's the main thing we're focused on. Refocus this a little bit. There we go. All right. So V final, maybe I need it, maybe I don't. V average, no. Okay. So I'm going to look at the equation sheet. I'm going to try to find one that has A, V initial, T, and delta x in it, but delta x is what we're looking for. So that's L grande. That's delta x equals 1/2 AT squared plus V initial T. All right. You could find the final velocity, right, by using acceleration and time. It'd be 2.5 meters per second squared times 8.2 seconds. That would get you the change in velocity. But this is a more direct way to do it. So now we'll substitute in 1/2 of 2.5. Now, since I've listed the numbers here with units, I don't have to put the units in my substitution. You got to be careful about that. If you don't list the variables out with units, you would need to put the units into the equation when you substitute in. It is a good practice to substitute in units to make sure things cancel out properly, but it's not something you always need to do. Alright, so anyway, I'm going to finally remember to bring my calculator home. 0.5 times 2.5 times 8.2 squared plus 5. Move over here. Plus 5.0 times 8.2 equals 125 meters. So let me just do a sanity check, make sure I've plugged everything into my calculator properly, right? 0.5 times 2.5 times 8.2 squared plus 0.5. It's not letting me scroll over. That's unfortunate. I'm gonna assume it's correct. If you had your graphing calculator, you'd be able to scroll over and get a better look there. So 125 meters. Great. So that's a good one. Classic El Grande. Try to get this to focus a little bit better on those letters. There we go. That's a little better maybe. All right. Kilometers. Okay, we better do this one so you can know how to deal with kilometers. That looks like a good one. A truck rolls 3 kilometers while changing its speed from 5 meters per second to 18 meters per second. At what rate did the truck accelerate? So that's our delta x. 3 kilometers. This is our initial speed, v initial. That's our final speed. And we're looking for acceleration. All right, so I'll make our organizational chart here. 3, 4, 5. V initial, V final, V average, acceleration, displacement, and time. V initial 5.0 meters per second. V final 18.0 meters per second. Average velocity, what's the average of 5 and 18? So 5 plus 18 is, let me put my calculator on the screen so you can see. Actually, I'm going to move over a little bit. There we go. I'm actually missing Mr. Robato's projector because I have to keep my phone kind of far away from the page, which makes it a little bit hard for it to focus on it. When you zoom in, things get blurry when you zoom. But anyhow, 5 plus 18 divided by 2. Oops, that's not going to work right. 5 plus 18 is 23 divided by 2. Average velocity is about 12 or 11.5. Does that help us? No, not really. The displacement, 3 kilometers. 3 kilometers. What the heck is that? Well, a kilometer is kilo. 3 km is 3 times 10 to the third meters, which is 3,000 meters. So delta x is 3,000 meters. This is the v final squared equation. V final squared equals v initial squared plus 2a delta x. That's the equation you need to use. There's really no way around that one. The timeless equation, it's also called, because we don't know the time. You could figure out if it's going to average velocity of 11.5 meters per second. You could figure out the time it takes to go 3,000 meters and then find the acceleration, but it's just easier to go here. And this is a bit of a pain, right? Neither velocity is 0, so you can't eliminate a variable. So I'm going to plug them in. It's going to be a little bit of algebra here. So it's 18 squared equals 5 squared plus 2a times 3,000. All right, so let's go ahead and find 18 squared. 18 squared is 324 equals 25 plus 6,000a. All right, so the 25 is going to have to come over here. 324 minus 25. And you can see how these Regents questions get tricky real fast. It's not even the physics that's hard. It's the algebra and the math that they add this extra stuff into that makes it hard. All right, so 324 minus 25, because I got to bring it over here, is 299. So I'll bring this up here. 299 equals 6,000a. So I divide both sides by 6,000. Divide by 6,000. And I've got a equals 0.05 meters per second squared. And of course, they can't just give me the answer in decimal, right? They actually need scientific notation. So how would you write this in scientific notation? A equals, well, you'd have to bring this over 1, 2. So it'd be 5 times 10 to the negative 2 meters per second squared. So that's answer 4. Wow, that is something. All right, so that's kind of interesting. Let's see. That one, number 7, a ball starts from rest and accelerates uniformly at 4.0 meters per second squared as it rolls 60 meters. So that's A, starting from rest. So that means V initial equals 0. I like when things start from rest. That makes life easier. 60 meters down an incline. That's delta X. How much time? This is going to be El Grande. You're going to solve for T. So delta X equals 1/2 AT squared plus V initial T. All right, that term goes to 0 because initial velocity is 0. Delta X equals 1/2 AT squared. Delta X is 60 meters. Now this is if you're not going to write them out, all the variables, right? 60 meters equals 1/2 of A, which is 4 meters per second squared. You would have to substitute in with the units. If you do this, just write it next to the equation, which is what a lot of kids will end up doing, and you identify the right equation, you absolutely must plug the units in with variables, all right? With units, I'm sorry. Must plug the numbers in with units when you do it. And then we solve for T. So, you know, we can take half of the 4 first. You don't need to carry the units throughout your whole calculation here, actually. That's something important to note. So multiply both sides by 2. Boom, boom. Divide both sides by 4. And then you're actually going to have to take the square root of each side. And you're going to get T equals the square root of 2 times 60 divided by 4. And radical 30. All right, which is 5.5. Which is, well, 5.47, so it must be that one, I suppose. All right, so see if you can finish up the rest of these. I should have maybe done this one. Let me see here. An object begins from rest and accelerates at rate A while traveling distance D. Which of the following equation correctly expresses the object's time of travel in terms of A and D? All right, so very interesting. So delta X equals D. A equals A. And you're looking for T, and V initial is 0. So this is another way you could go about doing this one. Organize these problems. You don't need to make this chart. You could just list them like this. This is what you have. That's what you're looking for. And if it's not listed, then it's not something you're going to use. So I know delta X. I know A. I know V initial. I need time. That's El Grande. Delta X equals 1/2 AT squared plus V initial T. And this is kind of a cool one. You're going to plug in the variables, the letters D for delta X and capital A for lowercase a. I really like this question, actually. This term goes to 0. Then you're going to solve for T and see what you get. All right? I hope you all can do numbers 9. That's kind of more of the way that we've been studying kinematics. Well, there it is. Good luck. I'm going to make another video here for you guys about how to perform the lab and get that posted before the end of the day. I'm making this at night, this one here. Yeah, all right. Have a good one. I'll talk to you later.